Well, at this point, let's go to 2.6, typical structural analysis problems. I would like to give you some diagrams. Um, the dotted lines are assumed um, deformation of the beam member under certain load. So the one on the left is a cantilever beam, and the cantilever beam having a force at the tip or have a moment at the tip. The other way is a typical beam where you have the force happening in the middle. Sometimes the force, the concentrated force or the point force will happen at one side or another side. Then this picture on the bottom, it shows a distributed load is applying on this beam member. So that's a very common practice as well. For example, your roof will have main structural beams uh, handling the load. And if we look at the roof plate will create a distributed load on the beam members. Come back to buckling effect. So if the structure buckled, you have a ugly, sudden large deformation shape. Or if you have a short beam, then when you press it down, it'll just go shorter. It won't buckle like this. The picture on the right is a very interesting picture. So basically, you have a large beam supported at the bottom. It's a fixed condition. You can tell the top is freed boundary condition. So what is this? Well, I don't know if you guys some surprise. This is actually the simplest way to simplify an offshore platform. So an offshore platform on the top sides will have topside loads going downwards. The boundary condition, why we have a fixed platform, a fixed boundary condition, because the piles and legs going deep into the mud. So the force from the mud will create a fixed condition, boundary condition. It won't move anywhere. But on the top, when the platform is in the air with the water, there's really nothing stopping it from doing a lateral move or rotation move. So it's almost like a free boundary condition at the top. And then divided by the water line. So on the in the topsides area, we have wind loads. Wind loads are exponentially higher when the height is going higher. And wind loads are typically use 10 meter as the benchmark number, and you do a exponential equation to calculate the wind load. Current load is a one roughly universal. In general, in real practice, the current load will sometimes have some stepped change as well. Say, for example, at the top, the current load may be higher, and then they started going deeper at the bottom. But in general, it's pretty uniform. Wave loads, the top of the wave loads, where you have the most waves, the wave loads at the top, at the water line, is usually the highest, and then goes down at faster speed. And to analyze an offshore structure, you will need to know the self-weight, which I pointed at the middle going down. Foundation force in the very top of the mud line is smaller. Once it goes deeper, it goes larger. So this is the mud line, assume the mud line. Well, with that being said, let's look at this cartoon and look at it again to find out typical structural analysis problems analyzed here. So the first one is for planned lift of the compressor module, will the lifting sling break under tension? Well, this is the one. So we need to understand how much weight that compressor module has. And then in the meantime, we do a calculation of the tension. So the applied tension force on the sling. In the meantime, we check the capacity of the sling member to see if that applied tension has gone exceeding the capacity. If it does, then we may have a break event. If not, then we're fine. Or if not, then we can also calculate the factor of safety. So we know how much reserve we have in the bank. Similarly, if we check the flare, this is a flare structure, remember, the flat structure has a tendency to fall down. So the top member here will go in tension, and the bottom member will go in compression. Second type of typical structural analysis problem will be, say, if it is predicted a 100-year wave combined with current will impact the platform, the weatherman has said its word, will the pile and leg yield in strength? So will we have a failure there? We're talking about leg. The wave is coming this way from left to right. And if you can think about that, then if the bottom is fixed, roughly fixed, then this leg will have a tendency to get shorter because of the wave of the overturning. So it'll undergo some compression. And this one on the other side will have some tension force there. If we do the math and compare the actual calculated tension or compression, then compare that with the capacity, so we know whether it's good or not. Next question, typical structural analysis question is, for the horizontal I-beam supporting the deck, will they have enough strength for the bending load? We talk about it here. So this beam member is supporting the derrick. Is the derrick too heavy to fail this I-beam? The way we do it is to calculate the bending strength, the bending moment, and compare that with the capacity, similar again. And on the top side, people will use I-beam. And if you remember, we have strong axis and weak axis. We know the load is coming from the top, and we know I-beam in this way the strongest in this vertical plane direction. So that's why you see most of the I-beams will be laid out this way rather than an H shape. There could be members, say horizontal beams over here, having a horizontal beam force as well. In this case, we wouldn't know where the wave gonna come from in terms of direction. So that's why we have a round-shaped structure used when we don't have a strong axis or weak axis. The fourth question, for the vertical structural beam members, will it buckle under vertical load? So we come back again. If this is a member, and the question is, will that buckle? We have reviewed the critical buckling load equation. The way we work is to calculate, to assign the boundary condition, understand the embraced length, understand the material E and I, and do the calculation to find out whether there will be a buckling happening. Similarly, on this compression leg, the failure mode could be it'll buckle or it'll be overstressed due to compression. The last type of question is, will the member fail because of shear? Again, this crane is a good example. We know the force is coming down this way, and it's trying to shear this member. So if the member shear strength is not enough, it could.